because we use them so often, there are certain binomial products that you should really know by heart. So rather than us either using the distributive property or the FOIL method, we will be looking at some of these by the pattern that they make, and ignoring or avoid using the longer approaches of distributive property and or the FOIL method. So the first one, which I'm pretty sure that you are familiar with, is the sum, is the product of the sum and difference of two terms. Sum and difference of two terms. What do I mean by that? So if I said let A and B be my terms, if I look at the sum, this would be the sum of the two terms as a binomial, and if I multiply that with the difference of these two terms, well, let's see what we get from using the FOIL method. So using my FOIL, right, go ahead and use the FOIL method. We'll see what we pick up, and we should see that we have a squared minus ab plus ba minus b squared. Now, this brings up a good point. Remember that these AB and BA are really the same thing. It's just turned around. The commutative property does allow us to say that we have minus AB and plus AB. And here we brought back our A squared and B squared. Alright. Now, as we go through, these will cancel. And so we end up with A squared minus B squared. And you should know that this part is called the difference of two squares. Okay. Alright. There's another way of saying the same thing. Sometimes as math, or being in math, we get a little lazy in saying the product of a sum and the difference of two terms. We will sometimes talk about something called terminology. We will sometimes talk about if I have a binomial, we'll talk about the conjugate of A plus B it's the same terms but the opposite sign in the middle. And the conjugate of A minus B is A plus B. So if I go about, I can even write the conjugate of x plus 3 is x. I have x, I have 3, but I put the opposite sign, right? The conjugate of 2x minus 5 is 2x plus 5. So another way of saying the product of the sum and differences of two terms is equal to the difference of two squares. I can write this in a more compact way and say that the product of the conjugate pair is equal to the sum of squares. So essentially the pattern that we want you to pick up, we don't want you to go through, you don't need to, do not need to, don't need this step. This is going to appear so often that we'll just end up getting A squared minus B squared. And so what we will typically write is A plus B, A minus B, equal a squared minus b squared. Yeah, go ahead, ask. Okay. All right, so we have a question that someone is asking, what does this really mean, or where does it come from, or so on. All right, let's just give the proof of what this meant. Suppose I'm going to do my best now to draw a rectangle. Let's say each side of this rectangle has length, let's take a square. So it's a square of length A. If I now take out, if I now say, here I have, or fit in here, a little square of length B. So essentially I have this figure. What I want to do, and I say I want to find the area. So the actual figure is really a big box with a small box, or a small square removed. So I want to find what is the area of this. Alright. Okay, so each of these sides we said were A. This length here is B, that length is B. Okay, if we were to cut these in two, we'd have, especially if you did it, we'd have two equal, so area, or the total area is equal to area 1 plus area 2. But by symmetry, they are actually equal, so twice area 1. Alright, what shape do we have for each of these? Let me bring this out a bit more. What shape do we have? Right, we have a trapezium. The length, or these are parallel sides, and the distance that we have here is height, right? H plus B is equal to A, so H equal A minus B. How do we find the area of a trapezium? It is equal to a half the sum of the parallel sides. Wow, spelling has gone today. Sum of the parallel sides times the height, or distance, right? Distance between the sides. So this would be 1/2. We would have A plus B, those are the parallel sides, and the distance between them, or that height, is A minus B. So if I go back over here, I get that the total area is 2 times what I just found. 2 times is 1/2, A plus B, A minus B. So that cancels. I end up with the sum times the difference. Alright, let's look at the area in a different way. So let's look at this area in a different way. I could look at it as the big box, that is the big square minus a smaller square. Big square has an area, right? So big square minus a small square. What do I get when I do that? The big squared is a square. The small square is b squared. So I end up really getting exactly what. Right. So the geometrical meaning of this, the product of the conjugate pair is the sum of squares. It's just a way of finding the area of a large square with a small square removed. Alright, so that's all that is going on in this part. So that's the geometrical way of proving this difference of squares. Sorry, up here, can we make a correction, please? Definitely very wrong here. Not sum of squares, but difference of squares. Sorry about that. Okay. Alright. So the product of a conjugate pair is equal to the difference of squares. Oftentimes, this side I will just use the abbreviation DOTS for difference of two squares, and I'll either just talk about the conjugate pair rather than the longer way of saying it, the product of the sum and differences of two terms. Alright, now what this means is that we want you to recognize what's going on. So if I have a few examples, and if I gave you 2x plus 3 times 2x minus 3, while it's true that you could go through FOIL and end up with the answer, immediately what we want you to do is recognize that this is a product in the form that you are multiplying the conjugates or multiplying a sum times the difference. Hence, we have the difference of two squared. The first term squared minus the second term squared. Now work out and let's see what we get. We end up with, remember, each item in the bracket is squared. 2x, 2 squared, x squared. So 4x squared minus 9. Alright? If we look again, it doesn't matter how or what the numbers are. If I have, say, 5x minus, I make it annoying, and 5x plus 13y. Again, you have a difference times a sum. Right, the difference times the sum. And so we must end up with the difference of two squared. What are these squared terms? The first will be 5x all squared. The second is 13y all squared. Multiplying or getting rid of the brackets, 25x squared. 13 squared is 169 y squared. Right? So in both of these cases, your final solution contains no bracket. It's simplified as fully as possible, and this is what you get. There are times that although it's not a binomial, you are still going to be using this idea of the difference of two squares. And what do I mean by that? Let's look at an example. So here's number 1, 2. Okay. So if we gave you to simplify x plus y plus 2 and x plus y minus 2. I don't know if you realize that essentially what you have, these are the same terms, and you're adding 2 to it or subtracting 2. So it's a sum and a difference also. So let's write it out with brackets now. And sometimes when we do this, you might want to change the style of your bracket. So here I'm going to, what I highlighted before when I saw that pattern in my mind, I am putting in brackets. And what I'm saying to you is that this is now in the form a plus 2 or a plus b and a minus b. So I'm going to use the property of the difference of two squares. Right? So it's the first term squared, which x plus y all squared, minus the second term squared. So my a is really this x plus y, and my b is the 2. Right? So I have to write form. Alright, now we're coming up shortly to looking at that perfect square, but recall for the time being that this is two copies of x plus y. So while I can simplify the 2 square on the end, we now have to incorporate the idea of FOIL. Right, so use FOIL to find this, unless you have from previous knowledge, remember perfect squares. And so we end up with x squared, xy, yx, but that's the same, these will be like terms, plus y squared minus 4. We can combine these as like terms. And in combining the like terms, oops, don't want to go up too far, we have our final answer, which is x squared plus 2xy plus y squared minus 4. So it might seem a little bit unusual that here we have something that is not exactly, or it doesn't look like you have the product of a sum and a difference, but upon closer examination we see that this is true, right? So when we look here, we see that this line really had the correct form, and we were now able to apply our fast rule and get the answer. Alright, a question was asked that could we have done it using the distributive property, and the answer is yes, we could have. We'd end up with 9 terms in all, some of which would disappear. So it's a little bit easier here. The most that we ended up with were 5 terms in the second to last line, which later compacted to 4. So the idea is the more terms you have, you could have a possibility of errors, and so by using some of these special forms, you're literally cutting down on these errors, possible errors. Alright, so that's the first special product that we need to know. The second special product, I kind of sneaked it in there, and this was what we call, or this is what we call the perfect squares. Right, remember we're dealing with binomials, so I'm looking at squaring a binomial. And we could have started out with the sum. So if I had a binomial a plus b and I square it, let me just give you the forms and then we will show that these are different, that these are correct by using first the FOIL method. But I want to just write out the format: a squared plus 2ab plus b squared, a squared minus 2ab plus b squared, and talk about it a bit. Alright, in words, and what we're saying is that the square of a binomial, right, the square of a binomial always has 3 terms. And those 3 terms, well, let's just look at the terms in general. Notice that in both lines, essentially, the terms have the same format. I have a squared, I have b squared, I have either a positive or negative 2ab. but the way that the product or the pattern is the same, just maybe the sign would differ. Alright, let's look a little bit. If I have a plus sign, you notice that this is the same. Right? If I have a minus sign, these two signs are the same. Anything that is squared is always positive, so there should be no question about me having positive a squared and positive b squared. Alright, now let's, in words, let's look at these, the pattern that we have here. Okay, so let's describe the pattern for the various terms. So if I look at this, in the binomial, we're going to say, right, so the pattern. So in the binomial, on this side, A is equal to the first term, and B is equal to the last term. Now, let's look at the result. The result that we have, and we look at these patterns. This is the square of the first term. Down here, this is the square of the last term, the b. And as I mentioned, it didn't matter if I have positive b and I square it, it's still positive b squared, or negative b. When that is squared, it is still positive b squared. So there should be no question again regarding the sign or signs of a squared term. The only question should be when we have that middle term, what is the sign? And as I mentioned, if we started out with a sum and of a binomial sum, and we're taking the square of it, everything will be positive. All terms will be positive. If we're taking the difference, the middle term will have a minus sign. All right, but let's describe what is going on here, irrespective of the sign. It is twice the product of the two terms. Of the two terms. Sometimes I will just say twice the mixed product. Right, meaning that this is my shorthand way of remembering or saying it, but it's really twice the product of the two terms. The two terms in the binomial were a and b, the first term of which is a, the second term or last term is b. So whenever we have the sum, the way to remember it is that a plus b all squared is first term squared plus 2 times mixed product plus the last term squared. Alright, let's go ahead, and actually prove the first one. Alright, so let's see if we really get these answers, or am I pulling your leg? Right, so if I have a plus b all squared, recall that this will be a plus b times itself. There are 2 copies. I can use my FOIL method. I would have a squared, ab, ba plus b squared. What do I get? These are like terms, so I end up with a squared plus 2ab plus b squared. In a similar fashion, if I looked at a minus b all squared, we first write 2 copies of the difference using my FOIL method in the same way. The signs, watch them, minus AB minus BA plus B squared. I end up with A squared minus 2AB plus B squared, right? So it's, I haven't pulled your leg, but the idea is that when we see a form like this, when we see a binomial and it is a squared, we are simply going to use the format, which we will now memorize, as first term squared plus twice the mixed product, last term square in the case of the sum, or with the minus sign if it is a difference. Alright, so suppose we start off. Right, so if I started off with, say, x plus 2, let's not do 2, x plus 5 all squared. First term squared is the plus 2. You'll see I'm starting out the pattern. I know I have a square, it's a sum, everybody will have a plus sign. I will look for my first term. First term will be in these places. My second term will be in these places, and I'm just now going to fill them in. X, and 5, and 5. Expand, what do I get? I end up with x squared. 2 times 5 is 10x plus 25. So this is my final answer. While it is true, if you're unsure, you can check for first few if you get the same thing using FOIL, but I really need you to be able to go forward following the pattern, because we will be asking you to identify the pattern at a later date. Right, so what I'm doing here, I'm combining, I'm using my FOIL method, and you will see that indeed I got the same answer as before. But as the higher you go in math, it's not the answer that is as important, it's more learning the methodology, because essentially we're trying to master our tools and proceed. What I want you to notice, and big note, right, I can't highlight this enough, note that if I have, whenever I have, say, x plus 5 all squared, this is not equal to x squared plus 5 squared. There's always a middle term. This is why when I started out up here, I said that the square of a binomial has 3 terms. So it's important that you remember that all the time and recognize that the square does not just distribute across a plus or a minus sign. So none of this, right? None of this. Make sure not equal to. Alright, let's just do some arbitrary examples and see what we come up with. So let's do something a little bit more interesting than the coefficient being 1. So suppose we have 2x plus, let's do 7, alright, squared. Alright, again, first term squared, 2 times that mixed product, and the last term squared. Take your time, fill them in. First term was 2x, the last term is 7. Last term is 7 squared. Expand, get rid of all the brackets, 4x squared. Alright, 2 times 2 is 4, 4 times 7 is 28, so 28x plus 49. So that would be your final answer. Let's do one with a subtraction. Let's start out simple with a subtraction. X minus 4 squared. Right, same thing. Perfect square, first term square, but this time a minus sign. 2 times mixed product and the sum, last term squared. Right? Let's fill in just as before. This was the first term in those places. And if we're looking at last term, it is 4. We don't put minus 4, we just put 4. The negative sign has been accounted for already. And so we get x4, right? So x squared minus 8x plus 16. Alright, should we try it where we do something crazy now with it? Alright, so now let's do one more with a subtraction, and then we'll see what interesting things we can do. Alright, so 5x minus 4y all squared. So we could have worked in one variable or two variables, it doesn't matter. It's still a binomial, it's a difference. We'll still have the same pattern. Identify your first term, be minus twice that mixed product, and the last term squared. Fill in, might be annoying. 4y is my second term or last term. And now expand and get rid of those brackets. 25x squared. 2 times 5 is 10. 10 times 4 is 40. X times y. So I'm multiplying the complete thing. All the product of all the numbers or the coefficients. 2 times 5 times 4. And x times y. Now, next I am using my rules of indices, the power of a power. Each of these were to the first power inside. So recall that when you have a to the mn, it is that the powers multiply. So I'm applying that as I have earlier. And we ended up 4 squared is 16, y to the second power. And so again we have gotten that. Alright, just as I pushed the limit the last time, we can also give you something of this form. Say 2 minus x plus y all squared, right? This is in the form, so as we look at it, it really is already in the form a minus b all squared. So I'm just going to use that. So I have the first term, my a is just 2 minus 2 times this 2x plus y. Aha. So this is a neat one. Right, so here is my first term. So here's that first term, not the 2 on the outside. My second term or last term of the binomial, that's what we are using. And the 2 was just the coefficient of that middle term. So no problem in here. This is 4 minus 4 times x plus y. Right. This is also a perfect square. So I can use my I can expand again, right? So I would have, let's just bring that back down, and I would have this form, right? And we know what that is. Alright, so what do I get? This is 4, distribute the minus 4, so minus 4x minus 4y. And using my perfect square, x squared, right, whoops, sorry about that, picked up the wrong pen. Okay, let's pick up the highlighter. So this is my perfect square. I'm going to be using the form x squared 2xy plus y squared. Here's an item that is in this is in descending form. I'm sorry, ascending form. I'll just leave it in that form, right? Because we are starting from the power, 0 power, then 1, and then degree 2 terms are listed. When they like terms, then we list them in alphabetical or lexicographic order, but this came out quite nicely, right? Alright, so those are some of the special products. For those of you who are continuing with the next term, we are also going to be using some special cubics. Alright. So if I have a binomial a plus b to the third, the form, I'll give you the forms: a cubed plus 3a squared b, 3ab squared, and b cubed. If it's a difference, numbers are the same, or the coefficients, or the format is pretty much the same, but the signs will alternate. And 3ab squared, right? Okay, so let us look at how we came up with this. So if I have a plus b cubed, right, so proof. This is a plus b times a plus b, 3 copies of the sum. Let's find that product. And even though I've written it out, I know what the answer should be already. It is first term squared, 2 times that mixed product, and last term squared. That'll make my life easier. Alright, now I'm going to distribute. Right, so I'm going to multiply throughout by a. I get a cubed, 2a squared b, and ab squared. So I've done the partial product by a. Now let's do the partial product by b. And I'm going to be using, this is why I like to teach the vertical form. I'm actually going to make my life easier rather than hunting for the various terms. Multiplying throughout by b, I got a squared b, so I'm going to write it underneath, like terms underneath each other, 2ab squared and b cubed. So if I now add, I end up with a cube, 3a squared b, 3ab squared, and b cubed. Alright, which is exactly what we got there. Alright, many times we don't want to, we've done so much work there. We want to also prove a minus b cubed. And what we can do is we can say, alright, let's look at this as a plus negative b, to the third power. And so in the previous lines, wherever I have b, I'm going to replace b with minus b. So that will make my life a lot easier. Alright, so because this is now written as some sort of a sum, I'm going to use the previous part. So I have a cubed, 3a squared, but instead of putting in b, I'm going to put in minus b, right? Okay, and I continue. 3a, and I'm going to insert negative b for b. Go again. Negative b, and this time it's squared. Right. I am using, just in case you're not following, I am using this line or line up here, whichever one. And finally, the last term, so this time there are 4 terms, and I'm using minus b to the third power. Third power. and I substitute minus b. Okay, let's give ourselves some room. I'll just pull down when I need to compare. And now let's work out. So a cube negative b. That whole answer would be, or the whole term would be negative 3a squared b. Negative b all squared is positive b squared, so I get 3ab squared. Negative number to an odd power is negative, so I end up with minus b cubed. So you see here the signs are alternating, right? Alternating sign. Whoops. Signs alternate. Right. So positive, negative. So negative, positive, positive, negative. Right? So when we're doing the cubes, it's important to just remember, or typically what I do, I just remember the form of the sum, and then recall that the difference will just have an alternating sign. Right? Always starting with a positive. Alright, so let me just write the two forms again so that we can, or I'll just write one. A plus b cube is a cube 3a squared b plus 3ab squared and b cubed. Let's look at some of the patterns so that you can remember it also a little bit better. Let's look at the powers on a. Right, powers of a, they go from 3 to 0, right? You might say, oh, hey, where's that 0? So if I stuck in here a little a to the 0, 3, 2, 1, and it's 0. So the powers of a are decreasing. All right, let's look at the second variable, the powers of b. Well, although you only see it from 1, 2, and 3, there really is a b to the 0 here. So it's actually increasing. It's increasing from 0 to 3. Now, the power here is 3. Let's look at the degree of each term. The degree here is 3. 2 plus 1 is 3. 1 plus 2. Again, we get a degree of 3. 0 plus 3, or the 3 that you saw. So every term or every part of this has a degree 3, just like the power that we had raised it to. And the coefficient of the two middle terms is 3, right? So let's see if so writing it a little bit less cluttered, a plus b, the highest is start a cube, coefficient is 3, the a's are decreasing, so sometimes we'll see people do this, 3, 2, 1, and nothing, right? The b's are increasing, so in order to have a third power, then this is what we have. The coefficients for the middle terms are both 3. Right? So you can use these as a way to remember the pattern rather than us sitting down and working out each time using the 3 factors or so on. Alright, so let's see if we had, say, 2x. Let's start out easy. 2x plus 1 cube. And let's look at the pattern. The first term, 2x to the third. 3, 2x squared. And 3, 2x, 1 squared. And 1 cubed, right? What we're doing here is we're saying let a equal to 2x and b equal to 1, right? So take a moment, look and see that indeed these are exactly the same, right? It aligns exactly with the pattern that was shown above, and we have this. This is the last place that you're going to see these perfect or all the powers of the terms being degree 3, right? Because of having the constant there rather than another term. So it's important that you get this form correct so that you can continue. Right? So what I was saying, this is last place that you're going to see 1 plus 2 is 3, whether here or here. Yeah. All right, let's work out each part. 2 to the third is 8x cubed. Remember, we have to square first before we multiply by the 3. So 2 squared is 4. We get 4x squared. Let me even slow down on this since this is the first one. 3 times 2, no problem with that. 6x and 1. So let's complete this part. 8x cubed, 12x squared, 6x and 1. Right? All right, let's go again with, say, go to this. I may regret this, but anyway. All right, what do I get? First term cubed. So the pattern, my A is x, my B is 4. Use the pattern above. Right, and now let's put in x, 4, x, 4. Work out each part, x cubed. We end up with 12x squared. 4, 4 is 16. 16 times 3 is 48x. You still have to remember your order of operations. That is, squaring. This must be done first before you multiply. Right? So 4 squared was 16. 16 times 3 is 48, which is what gave us that middle. One of the middle terms, second to last term. Right? All right, same idea if we are taking a difference, and then after this you can practice in your workbooks, etc. Oh, cube. Sorry, that would have made it too easy. And we would have the first term cube. The signs alternate. So plus, minus, 3 squared. And plus 3x 2 squared, and alternate, so minus 2 cubed. Alright, so check your signs first. Plus, minus. I've gotten that right. First term cube, then the second term is 3 times the square of the first and second, and it's the right pattern. 3 times the first term, the second term is squared, the last term is cubed. That gives us the 4 terms. 3 cubed is 27, x cubed. 9 3 is 27, and 2, that's 54. 4 3 is 12. 12 times 3 is 36. And minus 3. Okay, keep practicing these products, and as I said, you should have lots of them in your exercises to look at. All right, we will do one last one. So suppose I have 3x minus 2 squared. Let's do x plus 2 squared. I'll do all sums. and then say 5x plus 2 cubed. Alright, so we want to simplify this. I'll give you a moment to try. For those of you who are just following us on video, you might want to pause, work out, and then resume. Okay, with me, I will just use my two. I'm using the special products, and just the same format that we had used earlier for both cubes and squares. Perfect cubes and perfect squares. Because of the factor of the 5s and 3 here, I will have to be a bit careful, and this is why I'm coming down. Simplify. 6x squared, 12x, right, 5, 3x squared, 12x, plus 12. In fact, what I'm going to do, I'm just going to use my, it might be in the wrong order as I go about, but never mind. This will give me a way of simplifying. So as I go through, I picked up an extra term, 5x cubed. Alright, tell you what, no, I won't do that. Let me back up. I'll just go ahead the usual horizontal form, and then we will underline those things that are like terms and gather them. 12 5 is 60x, and 5 times 8 is 40. Combining like terms, let's identify them. So x squares, we have our x's. And alright, one more. Yes. Alright, I'm going to write it in descending order. So my cubics first, 5x cubed. Gotten that out of the way. All my squares, I have 3x squared and 30, so that would be 33x squared. So 2 terms down, you might want to make a note which things you have used already, just to keep things organized as you go along. It's quite easy to get confused or confuse yourself. Try not to. 72x, and I combine the terms with x, and now when I combine the constants, we have 46, 40, 52, and 5, so 57, right? So I have all of these, right? Okay, and we'll stop there for today.